see what we can cover in the next 45 minutes or so. But I want to go back to this question, is manufacturing really important? Right? We're talking about the vehicle, we're talking about fuel efficiency, that's where the center of gravity is. Is manufacturing important? Where does this metal manufacturing pollution come from? And what are people thinking about in terms of environmentally benign manufacturing today? And we'll talk about some alternatives to subtractive manufacturing, additive manufacturing, and ask the question, is the future of environmentally benign manufacturing, EBM, a net-shaped future? And give a case study if we have some time. When we talk about metals manufacturing, and not everybody in here is familiar with the life cycle of metals, even though we may be mechanical engineers. Primary metal production after extraction. So basically, we pull it up out of the ground, we refine it, we purify it, we may cast it, then perform certain operations like cutting, grinding, finishing, electrical discharge machining. There may be then some preparation prior to painting. So we call that metal preparation. Get the surface ready for painting. Then there might be some painting or other finishing operations we'll talk about later in the term. Let's say in the next session, actually, we'll start talking about those issues. Assembly and then use. The assembly, you might have a lot of welding and a fair amount of energy consumption associated with it. And hopefully there's some recycling. Hopefully there's some reuse and remanufacturing in here too. When we talk about the metals life cycle, metals manufacturing life cycle, we're talking about these operations. Okay, so the answer is manufacturing environmentally important. I ask you. Here's our case study. Here's the front end of a Volvo. This front end was analyzed both made out of a composite, glass mat thermoplastic material. The final mass was 4 kilograms. There was about a third of a kilogram of scrap, leading to a final component weight of 3.7 kilograms. This is a galvanized steel front end, galvanized, of course, for rust protection. The material consumption was 9 kilograms. 3 of that was scrap, leading to a final part weight of 6 kilograms. Of course, you can't mold the color directly in as you can with the composite. So therefore, the galvanized steel needed to be painted, and there's a painted surface area of about half a meter square. Question to you, which is more environmentally friendly, the composite material or the galvanized steel material? Who votes for the composite? Got 3 or 4? Tentative 3 or 4? Steel? 5 or 6? How many don't know? Have been too often surprised by the answers that I give.
Can we say equal?
Okay, say equal. Sure.
Do we assume they both use about the same amount of energy?
No,
Oh.
absolutely not. This one is 6 kilograms. This one's 4 kilograms.
That's material consumption?
This is the final component weight.
How much energy do they use to be produced?
Oh, I don't know.
Oh.
Which one uses more?
That's what I would ask.
I ask you.
Probably
You know now.
probably
We showed the data here.
What about to recycle it?
Okay. So it seems that on the next slide here, here's our our life cycle stages. Here's production, and here's end of life. Okay. And the units here are a unit of impact assessment. And talk about the tricks of coming up with these types of metrics. They are flawed. Are they better than nothing? That's for you to decide. And basically taking inventory data, going through this impact assessment, 3 stages: classification, characterization, and valuation. Right, coming up with a value system for global warming versus solid waste, for instance, and coming up with environmental load units. This was done in Sweden in conjunction with the government there. Well, here's production. Certainly a lot more energy to produce the steel part. You've also got painting involved. So more environmental impact associated with the production stage than associated with the glass mat thermoplastic, which has a lot less energy going in, and no painting. Don't ask me about cost, because the GMT is certainly going to cost a lot more. End of life, however, as you pointed out, the glass mat thermoplastic is not economically recyclable, barely technologically recyclable. Best case, if you will, it's incinerated. Problems with incinerators, another topic for later in the term, but you can recover some of that energy, get it back. Certainly not as much as you would recover in recycling. And in this investigation using environmental load units, if you add up the production and end of life, it's about a wash. Right? Certainly within the error of whatever it took to produce this. Question?
Yeah, did they ever consider the durability of this material? Like if steel lasts 5 years but the composite lasts 20 years?
Both will outlast the powertrain.
Okay.
So probably not an issue then.
What about repairability?
Certainly doesn't factor into these numbers, but if you're building a practical vehicle, of course, these are real issues. A lot of where these materials are being used in vehicles now, plastics, you've got throwaway items in a lot of cases, right? Dent the side panel of a certain vehicle, they'll just replace it, not repair it, right? So do you have some excess consumption of material? Maybe.
On composites, is there anything going into where they actually design the composite for incineration?
To be more friendly in incineration. They haven't gotten that far in actually designing them for actual use application. So my gut would tell me probably not. But what are you going to do? You're going to burn it. And it's going to have some reinforcement in there. So whatever that reinforcement is would have to be somewhat more benign than what's already there. Whether it's glass, could be natural fibers, for instance, for reinforcement. You might think would be more incineration friendly, but I wouldn't even want to go there. I don't think enough work's been done, but I don't know.
Composite is going to go one of two places, right? It's either going to be burnt or it's going to go in a landfill. There's nothing else you can do with it.
Not economically, right. By the environmental load unit scheme here, you've got product use dominating once again. Right? Here's the glass mat thermoplastic. Here is the galvanized steel. Right? And these production and end-of-life impacts are barely showing up at all. So I ask you again, is manufacturing really important? Why we talk about manufacturing?
Are they different like that because of the weight differences between the two?
Well, part of this is that you're driving the vehicle around for 8 to 10 years. How long does it take to make a car? Not very long. Right? The manufacturing process in total is probably about a day or so. Of course, the material's coming from somewhere. It doesn't take very long. These are high throughput operations. Right? So is manufacturing important? You should be confused. Right? The point is, whatever pollution you're creating in production, and by incineration or what have you, that is being produced very locally. It's concentrated both in space and in time. Whereas the product use stage is spread out. You talk about the criteria pollutants, right? It's probably not a fair comparison at all. Talk about carbon monoxide in manufacturing versus carbon monoxide in use phase. If you live very close to where that carbon monoxide is being emitted in manufacturing, it is very concentrated. Right? Whereas, okay, the concentration factor for in use is not from a single vehicle, it's from all the vehicles going to the same place at the same time, and traffic, right? So these are very different things. If you're comparing carbon dioxide, that which lasts in the atmosphere for hundreds of years, it is fair to say that in use is the story, and focus there, right? But that's not to say that we don't have a tremendous amount of criteria air pollutants that are of concern in manufacturing, and solid waste, and aqueous waste. And it was, we mentioned earlier in the term, aqueous waste, manufacturing is the biggest, let's say, most intense polluter of aqueous systems. Question?
The environmental load units, the significant portion that is in the product use phase, if it's going to be eliminated anywhere, wouldn't it be in the design or production? I mean, you could design either maybe different...
It would be in the design. It could be in the consumer, too. If you had a completely different municipal infrastructure, right? The way your city was set up, people's habits, where they live relative to... I mean, there's a lot of ways to fix this, right? Technology is another way to fix it. But if you pull carbon dioxide emissions out, right? But nevertheless, I mean, the other criteria pollutants are also a function of how much fuel you burn. So go to a hybrid vehicle, right? Use less fuel, there is less pollution. Not just carbon dioxide, not just resource consumption, but criteria pollutants also.
I just want to make sure I understand what this is saying. During the product use cycle, the environmental load is less for a GMT composite front end because it
It's
weighs
lighter.
less? It's lighter.
It
Okay.
uses less gas.
Okay.
I think it's about 100 gallons over the life cycle or something like
Okay.
that. I don't remember off the top of my head.
Okay.
Yeah, significantly less. Yeah, 2 kilograms. So that's like leaving your golf clubs in the trunk, right? I mean, that's the weight difference over a long period of time, over 100,000 miles or more, right? That has a big impact. Is manufacturing environmentally important? Of course it is. We wouldn't be talking about it if it wasn't. It's not just about solid waste. Carbon into the atmosphere. If you look at chemical manufacturing, if we look at primary metals industry, together over 130 million tons per year emitted to the atmosphere of carbon. It's more than most countries in the world. Okay, and that's manufacturing, U.S. manufacturing. Good fraction of petroleum and coal products comes from the decisions we make in design and manufacturing, what we can manufacture with, what we choose to make our vehicles out of. Okay? And about 5% of electricity production, not carbon emission, but electricity production, is used to produce aluminum. I think the actual number is closer to 4%. Right? But that's a lot just for aluminum. Right? Talk about where that comes from in just a minute. Solid waste, about 7 billion tons per year from mining and manufacturing. Okay? So you have to ask, where does this waste come from? All right, so we're going to give a little tangent about where these materials come from. If we talk about steel, you should ask, where does steel come from? And again, if you're our typical mechanical engineer, you don't know. Right? And you wouldn't necessarily think about mining, right? The concentration steps, the blast furnace to make the pig iron, and then making steel from that. And these are energy and material-intensive processes. This is National Steel Pelleting. It's taken from their website out in Keewatin, Minnesota. Michigan used to be a big iron mining state. In fact, the capital of Michigan was going to be up in the UP because it was the economic center for a good long time. Shifted to Minnesota for iron in particular. Early in the in the 1900s, the taconite reserves here lower in concentration than some of the other ores that we had here in Michigan, but nevertheless, it's economic. We've got about an 8 square mile open pit here. It's very large operations you can get a sense of. This particular operation, about 5.5 million tons of iron pellets produced a year. Think about it. This is like a city, 85 megawatts of power to run these operations. And that's not the on the ground. This is to actually purify the pellets that are being produced on site here. So here's a sort of a diagram of how this works. And I think if you click on this, it'll take you to the website. It's all animated and stuff, and you can read more about it. Basically, you're blasting this iron ore out of the ground, and you got a big sort of gyration shaker here to get this down to the size of about footballs. Right? So you got a conveyor then, hold it in a hopper, and you're going to use a ball mill here to sort of grind this stuff up and carry it in an aqueous solution. You want it small enough so you can carry it. Moving this stuff isn't easy. If you can get it in an aqueous matrix, then it will be easier to move. If you can get it into small bits, you can use magnets to separate it. So there's a lot of magnetic separation going on here. There's also hydroseparation. So now you get this sort of pasty iron-water mix that then needs to be concentrated and thickened. You put some clay in here and some limestone. We'll see why the limestone's used in just a minute. Fire the pellets, stick them in a hopper, put them on a ship, and send them on down the Great Lakes to steelmaking operations, National Steel, for instance, in Indiana. Huge operations. Get a sense of scale. Why do we care? Well, mining is an issue from acid mine drainage. You unearth, remove the overburden from these ores. Now you've got sulfur. You've got the production of acids, in particular sulfuric acid now. When it rains, that free sulfur is going to get carried up in the in the runoff from that facility. You can imagine millions of gallons of acid water leaving these types of sites. Right? It's been estimated that about 10,000 miles of streams in the U.S. are polluted by acid mine drainage. You've just never seen them. right? How would you know? But people have compiled these sorts of statistics. Mine tailings are also a concern. You're blasting huge amounts of earth, if you will, right? So what are you going to do with the overburden? You're going to make mountains out of it. So they actually sculpt hills out of these materials. They try to match, environmentally conscious mining. They try to match the contours, so it's not quite so unsightly. They used to dump this stuff in the Lake Superior. And there was a big, famous court case with the Reserve Mining Company. They were dumping tailings into the Lake Superior. These tailings have quite a bit of asbestos in them, contaminating the lake. This is just to give you some scale here, right, where it's located. And of course, they had to pay some damages from the activity. Of course, now there is regulation associated with how these things are treated. Most of the waste, most of the tailings here are landfilled now. And there's certain landfilling techniques that are less damaging. Try to contain that acid drainage and some of the asbestos and other nasties, if you will, that are in the overburden. So you get these pellets, right? You ship them down to steel making, or let's say an iron purification operation. A question in the back.
I wasn't quite sure exactly what is tailings, mining tailings, tailings. What is it?
It comes from the ground that you blast up. So there's an ore beneath the ground, and you're going to stick some explosives in some type of a pattern. So you're going to go do some research, and you're going to drill some test holes, and you're going to see where a good concentration of iron taconite ore is. About 25% pure would be a good ore. Then you're going to set up a blast pattern, and you're going to sequence it so you can most efficiently remove that overburden, so you can get at it. Well, now, I mean, you can't just pull the ore out. You have to remove they call it the overburden from whatever was above the ore. So that's what it is. And then you sculpt these mountains out of it, and you got to do something with all those tailings. Right? Okay, so how do they get more purified iron? It's only about those pellets that are made are only about 2/3 pure in iron. So we want to purify to get pig irons. This is what a blast furnace might look like. Basic idea here is you take your iron pellets, you dump them in here at the top, along with solid carbon fuel and some more limestone. At the bottom, you put in hot air. The hot air is going to burn the solid carbon fuel. That's called coke. Imagine the emissions, right? This is beyond coal. Okay, it's pure carbon and quite a bit of emissions coming out of here. It's going to react to form carbon dioxide. The solid carbon fuel interacts with the oxygen to form carbon dioxide here at the bottom, right? And this is where the blast furnace is the hottest. As you move up, it gets cooler. It also has less oxygen. So it's a reductive environment up here and an oxidative environment down here. Carbon dioxide is going to interact with more solid carbon that comes into the top to produce carbon monoxide. Carbon monoxide is a strong reducing agent. And it interacts with our iron oxide, our somewhat pure iron pellets coming in at the top. And it's going to essentially reduce it to iron oxide. And that iron oxide then can, basically you can strip off the iron to form this calcium silicate oxide. So you've also got some sand in there, right, because you've blasted this up from the ground. So the key idea here is you're reducing this iron until you've stripped out off all the oxygen. Right? So you need a reductive environment to do that. Creating this carbon monoxide, here you can see these stepwise reactions, that one by one strips off those oxygens until you've got pure iron, which falls to the bottom. Right? Now some of the other reactions that take place here, limestone helps to form this slag, pulling off silicate also. So you add pollutant, what would contaminate your iron, to remove more contaminant. Right? And this can be 95% pure, 99% pure, depends. Okay? But imagine the temperatures, imagine the scale. Okay? This is, if you've ever been along the way, on the way to Chicago, you've seen these types of, along southern coast of Lake Michigan. You've seen these operations. They're massive. Okay, to make steel then, it's basically the same thing as a blast furnace, but you use some scrap steel here. So that's coming in here first. Adding molten iron. They melt the iron, put it in there, add some oxygen. And of course, there'll be alloying elements and a lot more complication here. But you've seen these types of converters before, right? Here is the molten steel coming off the bottom and the slag being poured off the top here. Give you an idea of scale. That's something you should be familiar with. Steel making operations in the old days before pollution control, right? I mean, there's emissions all over the place. Right? The solid carbon fuels, all the melting, metal oxide fumes, along with the ability to form pollutants that weren't originally there under this type of an environment. Lead, ammonia, cyanide, etc. Right? We have ways to control this pollution now. It's just smoke, blown smoke from steel-making operations. This was in the Tennessee Valley back in the 30s or 40s, I think, was when this was taken. Right? But this is in the days before pollution control. You see what, what the investments are, right? What would otherwise be. Right? Water pollution, and now we control these air emissions, but to a large extent we just convert. If you are familiar, and we're not going to talk much about it in this class, but actually on your CDs you have some notes about how these control technologies work, how a scrubber works. And one of the key ways to control air pollution is to create water pollution, right, in a way that is more easy to handle, in a form that people perceive as being more benign. And it is more benign. But it's control, it's inspection at the end of the day. Electrostatic precipitators, such as what we would see on a coal-fired power plant. About 5% of the electricity generated at a coal-fired power plant goes to electrostatic precipitation to control the pollution. So it's 5% waste right there. Okay. So think of it as an inspection process. Aluminum, I'll just really quick talk about aluminum and copper, some of the key metals that we use to specify. Aluminum is different from other metals in that if you put aluminum in a solution at high pH, it will precipitate. Other metals won't do that. Right, so the key to getting very pure alumina, and bauxite, which is the ore where aluminum comes from, is very abundant in the Earth's crust. Not too much concern about aluminum as a resource disappearing anytime soon. I mean, we can recycle it, one, and two, there's a lot of it in the crust. But it takes a lot of energy to get this stuff out. As we mentioned already, 4% of electricity used in the United States goes in the production of high-quality aluminum. Now, most of the bauxite is down in Australia. A lot of it comes from there. When we have the refrigerator example later in the term, you'll see where that actually comes from. Basically, taking this bauxite, you're grinding it up, removing some of the big stuff from the actual ore, and then in a solution, you're basically adding sodium hydroxide. A very simple process. You can do this in a Chem 101 experiment. You just, at high pH, you get that alumina precipitate, and it's going to be very, very pure, almost 99% pure. Not pure enough for engineering applications, but very pure. To finish it, to get perfect alumina, we go to, or near perfect alumina, you go to an electrolysis reaction. Okay, but key unique aspect of alumina is that you can use this precipitation mechanism at high pH. This is what a electrolytic cell to purify alumina might look like. This is molten cryolite in the light gray up here. It is sodium alumina fluoride, if I remember correctly, at about 800 degrees to melt that stuff down. It is another oxidation reduction reaction that you can't read here on the screen. Basically, you've got graphite and basically lined cathode here. And the reactions aren't really important, but what I want you to understand is that there is an electrical potential across the anode and the cathode, using a lot of electricity to drive the oxidation reduction reaction that produces pure aluminum that we just pull off from the bottom here. And a lot of fluoride emissions from the cryolite as you melt it. So just think of scale, think of energy consumption. This is an electrolysis process. It uses a tremendous amount of electricity. Okay. Scale, we use a lot of aluminum. Okay, so what are the pollution concerns associated with aluminum? Tailings, as with iron mining, But mostly we're concerned about the energy and electricity that's used. How do you prevent aluminum manufacturing pollution? The best way is to recycle aluminum. Right? The energy to recycle aluminum, that it takes about 1/20th, I believe, of what it takes to produce virgin aluminum. Right? And I think we know that. As we said for aluminum, high pH precipitation is a key to pure aluminum. I'll come back to you in just a second. The key for copper, to purify copper, the trick associated with copper is the fact that copper doesn't like water. Copper is relatively hydrophobic. So if I take my copper ore, and copper is found in a very dilute concentrations, down below 0.5% in an ore. Down in Mexico, for instance, there are copper mines that to a large degree have been exploited, and they're not environmentally friendly at all. I mean, even for mining. But the economically recoverable ores are less than 0.5%. So what do you do with that? Well, you can grind it up, again, remove some of the big stuff. But the key here is to get about 50% pure copper. What you do is you grind up the copper, and it will be mostly polluted with sulfide, but other pollutants will be there too. Grind it up really fine, and then put it in a emulsified bath, if you will. So you've got some oil and water here, along with some emulsifiers. And you can basically bubble through air and oil, things that are hydrophobic. So the copper grains will prefer the air-water interface and the oil-water interface over just being in bulk water. So it'll froth up to the top. So you get basically a copper float. And on your CD, you can actually see what one of these looks like. Okay. And you can get up to about 50% pure copper here. Right? But again, you're still going to have a lot of sulfur that has to be removed. So there is a smelting operation that can remove that sulfur, getting you almost pure copper. And you know that very pure copper is essential for the operation of electronics products. So again, you'll go to an electrolysis process. Some sulfuric acid, copper sulfate. As your electrolyte here, a lot of electricity used. Okay? So when you think electrolysis, again, especially at large scale, lots of electricity used. But in that smelting operation, you're getting rid of the sulfur and producing sulfur dioxide. This is near to one of the largest smelters in the world in Sudbury, Canada, Ontario. One of the tallest smokestacks there. And we'll come back to that smokestack later in the term. Sulfur dioxide is just plain toxic. It's not only a concern for acid rain. If you make a stack that's tall enough, get it up into the atmosphere there where it can get carried by wind, it will become sulfuric acid and fall out as acid rain. If you have a short stack, it will fall out sort of in a dry state as sulfur dioxide. Remember, sulfuric acid is H2SO4. And that's a conversion process that takes place in the atmosphere to cause acid rain. Sulfur dioxide is toxic. And you can see what it's done to the vegetation here. Toxic to humans, toxic to vegetation. So, of course, we need treatment processes or bigger stacks, which is how people historically. Remember, dilution is a solution to pollution. Tall stack dilutes out over a bigger area, right? And some treatment too. Okay, one question.
Just back on aluminum, I thought that aluminum is presented in a composite form most of the time, and so it goes back to the recycling. That it was easier to, it was more efficient, I guess, to recycle it than to pull it from the ground. How does the aluminum composites add to that?
Contaminants in aluminum and steel and in copper are a major issue. I'm going to have a recycling lecture later in the term, and we'll talk about exactly what knocks out a load of, say, aluminum from recycling. Right? Iron and copper. Copper is a knockout element for iron. We'll go through very directly. The issue isn't quite as much about taking pure aluminum that you might have alloyed in a certain way. And by the way, I didn't mention alloys. Right? I mean, that's a big part of the steel production What type of steel? 4041, 1018. These are different. So the alloying elements you have in the steel-making operation, is it a low-carbon steel or high-carbon steel? High-strength steel, low-strength steel. And blew all that stuff over. It matters, and it affects the recycling significantly. But it doesn't prevent recycling. And there's a large amount of recycling that goes on. But mixing alloys, mixing just plain materials, right? If I shred a car and I don't get all the copper out, some of the copper gets carried out with the iron, yeah, that iron's going to be a lot less recyclable, for sure. This is a huge issue. And one we'll talk about at length later in the term. Question in the back.
When a lot of stuff is put in the landfills, like you said, sometimes the mines get converted in landfills. Is there any study as far as what comes out of the landfill? If you leave it there for so many years, and all these things are mixed together, or like a soup, are any emissions going to come eventually out of that, or does that?
There's been a tremendous amount of work around characterizing leachates from landfills. So you get the rain seeps down, and then leaking. They try to line these landfills, and they do a much better job of that than they used to. Are you worried only about acid? No. If you're talking about even a municipal landfill, right, without some of the waste we might be talking about here, absolutely the gamut of chlorinated toxics you might be worried about, from plastics, brominated toxics leaching out. In fact, there's a leachate assay that's a standard people use to measure the pollution coming from what's the potential when you landfill something for it to leach out some toxics. This is almost a whole discipline of study. You look at environmental engineering. There's a sector of that discipline that deals with landfill engineering. And you're absolutely right. It is a soup, and that soup, something's going to happen over time. And is it harmful? Yes. Can you fully contain it? No. But we, of course, do a much better job of that than we used to. Will these liners last forever? They say, well, liner for a landfill is going to last 100 years. Okay. What about 150 years? What's going to happen? Right? Depends on our source of water. If we've solved the energy problem, could be a problem. Maybe it's not a problem. Again, we don't know. Excellent question. So traditional manufacturing is worth our time. And don't let anybody tell you it's just about the use phase. Concentration in time and space, and these are going 24/7, these operations are going. Right? Massively polluting. Major contributors to greenhouse gas emissions. Major contributors to both solid waste and managed waste. That waste which we recycle. Recycling isn't a clean process. It still takes energy to do that. It still takes resources to do that. Right? And manufacturing is the largest contributor on both fronts. Okay? And when we're talking about the life cycle of metals manufacturing, maybe it doesn't come as too much of a surprise. Right? And I'm going to move forward here. Here's our metals life cycle: metals extraction, metals production, manufacturing, use, end of life. One way to prevent pollution in downstream operations, right? So if I don't want to machine the metal, maybe in that manufacturing of let's call it the purification of the metal, when it's in a molten state, why do I let that metal solidify and then melt it again to cast a product? Right, look at a transmission casing, right? Continuous casting is that type of an idea. And to the extent that you can get a perfect cast that doesn't need any machining or finishing operation on it, well, you can avoid downstream operations. We call that net shape manufacturing, when a manufacturing process can prevent other manufacturing processes downstream from needing to be performed. And as long as that process to produce the net shape cast does not produce more pollution than the downstream operations that you are avoiding, then it's a good thing. So much has been said about net shape manufacturing and its contributions to environmentally benign manufacturing. I was involved with a paper that discusses some of the potential, a couple of papers now I think about it, the potential of environmentally benign manufacturing goals to some extent being met by net shape ideas. Now, there's a difference between net shape manufacturing and considering net functionality. Net shape manufacturing is about avoiding downstream operations. Net functionality is this idea of conserving the energy and effort that you put into the product in the first place. We all know the hierarchy: reduce, reuse, remanufacture, recycle. Where does that hierarchy come from? Well, it comes from saving the functionality and the energy that you put into it. Right? If you reuse a refrigerator, all of the materials that went into that refrigerator are conserved. Right? The manufacturing energy, the manufacturing pollution, the materials, the mining, all that's saved. Right? So we have net functionality. Remanufacturing, if I have a design change and I can just, suppose I have a computer that's going to the next model, right? I can just remove a chip, right, as people say. It's never that easy, right? But, reconfigurable, remanufacturable, right? Less pollution than making a whole new CRT, which has a lot of lead emissions associated with it. Do you need a new monitor? No, maybe all you need is a new chip and some more memory, maybe a new motherboard, but certainly that would be less pollution. Recycling we know about, right? But again, buyer beware. The hierarchy can be broken, right? Reusing a refrigerator is a bad idea. And we're going to talk about why a few sessions down the road. So, but there is an idea. There's net shape manufacturing and net functionality manufacturing, right? Here's casting, for those of you who aren't familiar with it. You can see just a lot of pollution. That's really the point we're making here. You can take a closer look when you look at your notes. You get a whole lecture on casting on your CD if you're interested. But basically, we're talking about that are used to mold molten metal. So maybe I've got a sand mold of a transmission casing, right? So something that's very large. You've got to handle that sand. That sand can't be reused indefinitely. It is reused to some extent. Some recycling technologies for sand are better than others, but you go through a lot of sand handling. 17% of the solid waste produced in manufacturing on the production of an automobile goes to sand waste from castings. Lots of molten metal. You also have to make the molds themselves. That creates some pollution. So you've got volatile organic compounds in the casting process, particulate matter, carbon monoxide and NOx, along with sand handling, wastewater, and a lot of energy. Right? But if it's net shape, right, you might not have to forge your product down the road. You might not have to machine it, right? Net shape casting as a technology is a long way away. It may never happen. It's a very difficult thing to do in an economic way. Die casting is probably a close process to that. Injection molding, right? And we'll talk more about these individual processes in the next session. Right? But again, to the extent that they can avoid the need to remove metal. Metal removal is pure waste, engineered scrap. Right? And of course, the cutting fluids that go into this. We'll talk a lot more about cutting fluids in our next session. Right? Avoiding downstream operations. Right? To the extent that you can have net shape machining, you may not have to finish with an electrical discharge process. Right? Electrical discharge machining, EDM, basically using high current, large amounts of electricity to make a very nice surface finish. If you can do that in machining, that would be a good thing, avoiding the EDM process downstream. Right? Of course, instead of moving down the chain, really we should be moving up the chain. Right? What if we had net shape mining? Right? You have your blast pattern and boom, there's a Buick. Right? Thermodynamic limitations to that ever happening. Right? So clearly, net shape manufacturing can only take us so far. And we have to, whatever material we're making, we should think about whether we can use it in a more efficient way. There are, when we talk about machining, we're talking about subtractive operations. Make a cast, usually that cast has to be machined down because you have excess metal, trim, flash, right, you're familiar with, even in plastic parts. Right, you've got to do some machining. But can you build up layer by layer your part directly from scratch? And there is technology, in fact, technology being developed here in Mechanical Engineering Department, U of M. Right. All right, so let's talk about cleaning and finishing. These are, I haven't met a student that's not been in industry who really understood metal cleaning and metal finishing. Right? These are very practical issues. We don't tend to handle them in academics. Right? But we have to say a few words about them because they're some of the most polluting operations in manufacturing. Right? It's not just casting. It's not just metal cutting. But we start to get into chemical releases here. Use of cyanide, for instance, in certain baths. Large energy consumption, as we'll see as we go through here. right? Really 3 steps we need to talk about. We need to talk about surface preparation. Before we paint, before we electroplate, we need clean surfaces. Clean surfaces either mean that you're going to use solvents, generally chlorinated solvents, which not only are bad for the ozone layer, but relate to the ground level ozone problems and human health hazards. If you try to move away from solvents, you're going to go towards water, right? And water has its own security issues associated with it, its own energy issues associated with it, its own costs associated with it, right? And of course, resource depletion. So when we're talking about clean, we're talking about either lots of water, lots of energy for sure, or solvents. Okay? Surface treatment, we don't tend to cover surfaces and the importance of surfaces in our mechanical engineering curriculum. But surfaces are critical, right? Surfaces is where the rust happens. It's often where the contact happens, right? So the lubricating performance of surfaces can be very important. The electrical characteristics of surfaces, of course, can be very important. And we'll talk about the wear and things like that as we go through. And some other things listed here. The appearance, of course, right? What does it look like? That has to do with the surface. So we'll often treat surfaces and sometimes seal them or paint them afterwards, coat them. Right? So 3 basic areas here. Alkaline cleaner, right? Soap is kind of alkaline, right? You wouldn't eat soap, right? It's got a high for the emulsification of dirt and oil. So a typical process will involve an alkaline cleaner up front, then a rinse. And if I'm looking at electroplating something, and you don't necessarily know what electroplating is yet, but it's a very common process used to make shiny chrome-like surfaces that have excellent characteristics, I have to get rid of the oxide. The surfaces of metals, there is oxide, a passive film that protects from rust, especially in aluminum, for instance. It's very natural to have that there, right? It can be a rust oxide also. The acid dip here, the next step, is getting rid of that oxide layer so I can plate it. So I get that conductivity back, and then I can electroplate it. You'll know why conductivity is important for plating in just a minute. Okay? And then there might be a finishing treatment. Maybe it's a sealant. Okay, so these are very normal, everyday operations. Painting, right? Coating, plating. These are. Let me come back to it. I'll have a picture of one later. Catch the stuff and then put it back into the system. Essentially, it's nothing fancy. Types of cleaning methods. I mentioned solvents already. I've mentioned aqueous cleaners already. There are other ways to clean. You can use a vacuum. You can pull the oil off the surface. You can use a laser to blast it off. You can use supercritical fluids. What's a supercritical fluids? Anyone know? Anybody heard of supercritical CO2 applications before? Yeah. Okay. You try definition for us?
No, I haven't gotten that far. Sorry.
Okay, well, it's actually becoming quite popular in pollution prevention applications to look at CO2, carbon dioxide, as a solvent. You might think that's weird because CO2 is everywhere around us and nothing's dissolving, right? But if you put carbon dioxide at pressure and at temperature, see, we're locked into thinking in our paradigm about standard temperature and standard pressure. But what if we put a carbon dioxide tank under pressure and elevated the temperature just a little bit, maybe to 40 degrees Celsius? Put it under maybe 15 bar of pressure. Well, it's going to become something that isn't really a liquid, and it's not really a gas. It's something else. It's pseudo-liquid-like. And we call that the supercritical state. And you probably breezed through this in Chem 101 too. But supercritical fluids sometimes, and in the case of CO2, can have excellent solvent characteristics. So I can remove oil using pressurized CO2. Fantastic, right? Because CO2 is benign other than its carbon dioxide effect. But of course, we're releasing a lot more CO2 in other places, in electricity generation and in vehicle transportation. So it's a low percentage of that impact in all likelihood. So we can talk about supercritical cleaning and plasmas. We can assist aqueous cleaning through electro-cleaning methods or mechanical cleaning, ultrasonic, or I'd vibrate the piece or use electricity to help get some of the deeper oils off. Of course, that's going to take some energy to do too. Okay, so these are various types of cleaning methods that one should be aware of. And especially right now, the hot button issue is moving away from solvents. Of course, the Montreal Protocol, Clean Air Act amendments are moving away from CFCs and certain HCFCs. So moving away from solvents, often we create other problems. Solve one environmental problem, we create another problem. Of course, it's a lesser environmental problem than an ozone hole. But it's important to know what we can do. For solvents, we can reclaim solvents. We can recycle solvents. In fact, a well-designed solvent system doesn't have to create an ozone problem. It doesn't have to either ground level or in the stratosphere. It doesn't have to be a risk to human health. But there are costs associated with recycling solvents, especially if they would otherwise be cheap. It might not be cost-effective to recycle. The capture systems, the capital, also involves some effort and maintenance and cost, too. But it can be done, and that's important to realize. You can distill them. You can use equipment with less vapor loss, and that's basically what it says here. Moving away from halogenated products to non-halogenated products. So it's the chlorine in general that we're worried about. And so TCE, trichloroethylene. If you remember, we went back to Lecture 2 when we introduced pollutants. We had this top 20 list. And they were all either metals or chlorinated organics. Right? I don't remember if there was anything else that weren't represented by those two categories. So moving away from chlorine, not only it has effect in the stratosphere, but also on human health. So getting away from halogenated products can be useful. Reducing pollution from aqueous cleaning, what we can do, typically what you'll do is you'll have this high pH bath of surfactants that you use as cleaning. Okay, so you got this cleaning, aqueous cleaner bath, and eventually the capacity of that bath to remove oil is depleted. Remember, surfactants are what's emulsifying the oil that was on your part, right? And you're eventually going to deplete yourself of surfactant. So what do? Dump the bath, of course, right? That's the way it's been done for a long time. Well, there are maintenance strategies. Membrane filtration that we've already talked about can be used to recycle aqueous cleaners too, not just metalworking fluids. Controlling the amount of extraneous oil in the bath. Of course, if you've got a bunch of oil in your cleaning solution and you're trying to remove oil, it's not going to do a very good job. A dirty cleaning solution isn't a good one. So we can filter it and restore its properties so it can clean again. We can recycle them. We can get rid of chips and fines. And we can replace depleted chemicals, too. We can add surfactants. If we were intelligent enough to know when the surfactant concentrations were being depleted, we could, in advance, resupply them. A lot of work, especially in the mid-'90s, went on in this area, and people understand it pretty well. Again, this is an example of a technology that's not diffusing very rapidly into practice. But the maintenance of aqueous cleaning baths is certainly one pollution prevention opportunity. You should be aware of certain types of metal finishing, cladding, case hardening, dip galvanizing. Probably most of you haven't heard of those before. Electroplating, electroless plating, chemical conversion, anodizing, protecting an aluminum surface. Aluminum anodizing is very common. Put a passivating film. It has resistance to electrical conductivity. It has a certain appearance associated with it, protects the metal. So anodizing is a very common conversion process, right? Converting the surface. That's what we mean by conversion. Of course, it uses a lot of electricity. Phosphating, phosphate conversions. Sometimes paint doesn't stick to metals. So what do? Use a phosphate conversion process, and that makes the surface spongy. And then it can absorb the paint. It can absorb lubricant also for if you've got a very intense metalworking operation, if you've got a deep pot. You ever wonder how you make those pots that sit on your stove? Right? It's a deep drawing process and lubrication. I mean, how do you just take metal? It's not formed that way from a molten state. It's generally drawn because the mechanical characteristics are better. You need lubrication, and often you might use a phosphate conversion process ahead of that to get the lubrication to actually stick. Okay, I'm not going to talk about those in detail, but we're getting into chemistry, which tends to be why you don't hear about it in mechanical engineering. But it's really an interface, right? The mechanical properties of the manufacturing process are related to the lubrication and the ability of lubricants to stick to surfaces. Okay, cladding, if you ever looked at a quarter, the whole surface isn't nickel, right? If you look on the inside, right, there's a layer in the middle. Basically, cladding is a mechanical process. You use heat and pressure to put basically one metal on top of another. Right? Just heat and pressure. It's a forming process. Case hardening is, there are two types. You can use nitriding or carburizing, using carbon or ammonia usually to harden a surface by diffusing certain types of atoms. It could be ammonia, it could be carbon at the surface. Okay. Dip galvanizing, this is common with zinc. You can just melt it and just run your parts through it and pull them out and let them dry. Right. These are different ways one can change the properties of a surface. Electroplating is very common, and it's especially polluting. It's basically the idea of passing electric current through an electrolyte solution. We talked about electrolytes early on, where we're talking about production of metals. These are salts. And basically, you can take a chromium bar and take the chrome from that bar and put it on a wrench, for instance, that may be over here, if both are dipped in. And I got a figure showing this in just a second. But you're using the aqueous bath to close a circuit. And that allows migration from your source metal to your target part. Okay, and that's what electroplating is really all about. And it's got a very high transfer efficiency, as it says here. But again, it requires very clean surfaces. Some of the mechanical effects, surface hardness, tensile strength, are affected by electroplating. It can change the way it looks, lubrication properties, as we mentioned, corrosion resistance, conductivity. Here's the figure that I was referring to. Okay, what you've got, if we're talking about chrome, this is an ionized electrolyte solution. And you've got basically a battery, a circuit here, a DC current, a voltage being established between your source metal and your target part. And maybe this is a chromium bar, for instance. Chromium can be reduced in aqueous solutions of itself. So you'll have a chrome electrolyte salt solution. What's a salt? Anybody remember what a definition of a salt is?
Can be split into positive and negative.
Yeah, you got it. Exactly. It's like table salt. It completely dissociates when you put it into water. Right? So when I'm talking about a chromium salt, you've basically got chromium ions in this solution. And they can migrate from the bar to the target. Right? And it is the passing of the electrons, basically your electron rich over here on the left and electron deficient over here on the right. And you basically get a reaction that puts the chrome right onto your surface. This is another example of an oxidation reduction reaction. We talked about this when we were talking about purifying copper, refining copper and refining aluminum. Same type of reaction. It's similar but different, and I've got that coming up. So yeah, it has some similarities, but it's not the same. There's no aqueous bath in powder coating. Okay. Well, before we get to coating, talk a little bit more about electroplating. Metals don't want to sit in aqueous solution very much. For instance, I know for lead, only about 5 parts per million of lead is soluble in water. If you put more than 5 parts per million concentration, it will precipitate out. So in a process like this, where you want a high transfer efficiency, you want to put as much chrome into this bath as you can. So how can you fool Mother Nature into allowing more chromium to be in that bath than otherwise would be soluble? You use constituents of the bath that are called complexers. Okay, complexers allow higher than the natural soluble limit of a metal in water to exist comfortably. Okay, call that a complexer. And one of the best complexers is cyanide. Right, and everybody's heard of cyanide. It's nasty. And in fact, what's particularly of concern when you use a cyanide complexer, and it's great from a mechanical standpoint and manufacturing standpoint, this stuff's robust. And the baths last a long time. It's not so sensitive to cleaning. I mean, it still is sensitive to cleaning, but not terrifically sensitive to cleaning. But you've got energy, water, and cyanide, all in the same place. And what happens is you get the formation of hydrogen cyanide. Right? You've got water and you've got electricity. So you get some electrolysis going on, some production of hydrogen. Hydrogen cyanide is a very favorable, if you got cyanide in a place and hydrogen in a place, thermodynamically they want to get together. And that's a gas. Right? So there's, of course, some concern over worker exposure to hydrogen cyanide gas. So it has to be controlled. Non-cyanide alternatives exist, but as I mentioned, they're not so robust, and they certainly cost more. So you go from a very robust process that can be used in a lot of different operations to non-cyanide applications that are very specific to single applications, okay, which is obviously an inconvenience, a cost, a hassle. Hexavalent chrome is widely used in electroplating, right? Chrome plating that we've all heard of. Chrome 6, again, produces this hydrogen cyanide gas. And it has this great combination of wear resistance, corrosion resistance, lubricity, high temperature tolerance, right? And finding alternatives to Chrome 6, again, is very difficult. Right? There is something called Electroless Plating. This does not use electricity. The source of electrons, rather than being from a voltage source, remember we're talking about oxidation and reduction reactions, so you need a supply of electrons coming from somewhere. Rather than that being from a voltage source, it comes from the chemicals inside the bath itself. The thing to know about electroless plating, besides the fact it doesn't use an external source of electricity, is that it will plate everything, not just what's connected to some supply. But the tank will get coated, plastics will get coated, metals will get coated, anything will get coated, just surfaces, right? And here come these chelating agents. Why do we need chelating agents? Well, the chelating agents, you don't have this target source sitting there anymore. The metals are inside the bath itself. And the chelating agents are what, just like the complexers before, they hold the metal in the solution, right? So imagine trying to get the metal out when you're done with the process. You got the chelated metals, right? So your bath goes bad. By the way, electroless plating baths are very sensitive, and they go bad with a high regularity. They're very difficult to maintain. So now you got to waste treat this stuff. You've got metals that are locked in to solution. And traditional waste treatment operations, which we'll probably talk more about later in the term, primary, secondary, tertiary operations, they can't get rid of the metals. So now it becomes hazardous waste that needs to go through some very complicated, very expensive, and polluting, in fact, treatment processing. Okay. So electroless plating is great for the electronics industry. Look at a circuit board. How do they get the copper down? Electroless plating, right? And it gets the copper to form a very nice film. And of course, we need those lines to get our computer chips to talk to each other. Widely used in electronics. Okay. I think I mentioned everything here. There are also organic compounds in here that are difficult to waste treat from traditional processes. Oh, and because the tanks get coated also. So if I'm using a copper electroless plating process, the tank's going to get coated with copper too. Well, you know, it can't be like your freezer, right, where it just kind of comes down to zero. You got to control the amount of copper on the walls. So you have to strip it down. And that creates air pollution of its own, in particular NOx and nitric acid releases. Okay, so we're beginning to talk about some pretty nasty things in finishing. And we should probably talk about how one can avoid the need for cleaning and finishing. And we'll get to that later. There are alternative coating processes. They generally involve either the use of vacuums, chemistry, or thermal spray. Okay, but I'm not going to talk about them because they're not that widely used. I'm going to show the costs here. They all involve higher costs. Right? They're all proven. You can replace plating and cladding and case hardening with these types of operations, but they tend to cost more, even though they have lower EHS risk in almost all cases. Right? EHS, environment, health, safety risk. Okay. So they're not widely used right now. Are there any questions there before we move on to coding? Okay, a lot to absorb. But again, you get the idea. We're at the interface here between chemical engineering, pollution prevention, mechanical engineering. and materials, of course. Well, everybody's painted before. Has anybody here not ever painted anything before? Okay. So you know that paints smell bad. And if you sniff them long enough, you get a headache, right? Some people like that, right? I don't know. You ever try to clean a paintbrush before? That's not easy. What's the best way to clean a paintbrush? Throw it away. Yeah, okay. Got me. Second best. Don't let it dry?
No, well, yeah, that works, but let it dry and peel it.
Peel it with your hand? That's the environmentally friendly way. It's not that easy.
It's fun.
It's not that fun. I know, because my father and I, a few weeks back, we did an epoxy coating on the garage floor. And I bought a new paintbrush to help us out. And so I tried to clean that the other day. That was kind of tough. I was really looking for some chlorinated solvents at that point, because that's going to work great. So you get the point, right? If you want to clean, right, solvents, these solvents are great and they're cheap and you can use them, but it probably is more environmentally friendly at that point to throw the brush away and buy a new one. So I won't be painting for a while, I guess. I got a good excuse now. Anyway, rags, of course, brushes, rollers. You get some of the things going on here, right? Alkaline solutions, solvents, right? Same old story. But we should take the time to know what paint is and how it's applied. There are 3 different ways to apply paint. Here's a dip immersion method. So sometimes you'll see on car bodies being painted this way. You can have robots doing it, or you can actually have the whole body of the car on a conveyor, and you dip it in and kind of let it dry. Drag-out tanks and drain boards are used. Here's a drain board. So as the part drips, it falls back into the tank. So that's a recovery mechanism, a reuse mechanism. You might also have a tank over here to capture some more of it. That'd be called a drag-out tank, because it's being dragged out. A spray booth. Anybody seen a spray booth before? Yeah, it's pretty nasty. And you've got all sorts of personal protective gear if you want to go near it. These is an automated process shown here. And here is powder coating, basically putting a high voltage between a powder-based paint and the part itself. So you can see the part's grounded. We've got the voltage here, a very high voltage applied at the paint source. I'll show some examples of this later. And magic attraction between the paint and the part. Then you cure it, the paint on the part, and you've got a coating. What is paint? Basically 4 different types of ingredients in paint: the solvent, the binder, the pigment, and the additives. And if we look at a typical paint formulation here, the solvents will be about 60% of the formulation. Toluene, xylene, methyl isobutyl ketone. A lot of similar formulation in gasoline, right? And breathing that isn't good. And again, the bulk of the formulation in the traditional paint. Binders, I'll talk more about what binders are in just a minute, but they provide a lot of the working properties of the film as it dries, about 30%. The pigments, 7 to 8%, and additives, just like cutting fluids, have a lot of additives. Paints also have a lot of additives. And normally we're worried about the solvents, and we're worried about the heavy metals. There are very good pigments that have metals in them, cadmium and lead in them, right? Lead-based paint, you've heard of leaded paints, of course, being a concern. Solvents are used because they disperse the constituents very nicely. I've talked about dispersing oil in water. This is much the same thing. They also reduce the viscosity. That's important because you're going to apply this with a brush. So it has to have a good low viscosity, but again, not too low. Of course, the solvents themselves are volatile, toxic, and explosive, which isn't a great combination of characteristics. They also volatilize, right? Solvents, they vaporize. They have a very low vapor pressure. They contribute to ground level ozone, and they are classified as hazardous air pollutants. So certainly paint is a big issue. Binders are liquid polymers. They're resinous, and they hold the pigment and additives together. Right? The color and the additives have to be held together, and the binder helps do that. It also helps the paint stick to the wall or to the part, the adhesive properties. And the plastic film properties, right? The formability of the paint is also driven by the binders, right? The working properties of the film, as it's written here. Pigments give color. They improve the substance's environmental stability. We mean with respect to UV usually, right? So the paint doesn't start to peel or it doesn't fade with time. Okay. So UV stability is important. There are different types of pigments, of course, organic pigments and inorganic pigments. Inorganic pigments tend to be a more robust solution. Organic pigments tend to be brighter, but they're more sensitive to, again, like UV radiation. Right, some of the additives we'll talk about, especially for water-based paints, surfactants, thickeners, biocides. Bacteria can grow if you got water there. Coalescing agents, defoamers, plasticizers, flattening agents, flow modifiers, stabilizers, catalysts. You get an idea. These are complex mixtures, right? A lot of energy, a lot of effort to make a paint and to keep a paint stable. So when we talk about robust formulation, what do we mean? Well, we mean keeping all this stuff happy, living, in harmony next to each other. There are alternative coatings. You can, of course, try to get rid of the need for coating in the first place. You can try to reduce the solid content, or I'm sorry, increase high solids coating. You reduce the solvent content. So instead of 60% solvent, what if we could get away with 20% solvent or 10% solvent? So the solid concentration goes up. So we call that high solids coating. Or just go to water. Or use a powder coating process. Right? Or deliver that paint in supercritical CO2. Right? Or cure paints instead of using heat, you can use radiation. It tends to use a little bit less energy. Right? Surface free of coating, right? Coatings may not be necessary. What if you use a plastic part instead of a metal part, right? Here's the wax dinosaur again. Last time it was red, I think, right? This is a yellow one, right? The point is that the color is molded directly in, right? There was no finishing or coating operation on this plastic dinosaur. An injection molding process is one way to get rid of the need for coating. Certain metals, like aluminum and titanium, they have great surface characteristics. And you can actually create an appearance without a specific coating. For instance, anodizing aluminum can give it certain rather cool metallic-looking colors, right? Not without energy, of course, but there are ways to get around coating. Improved engineering functionality, right? If you've got inherent rust protection, often we paint because we want to protect from rust, right? Especially with cars. Well, what if you had materials that don't inherently rust, right? That's another way to get around the use of coatings. Going to water instead of solvents, right? Sounds great. It can lower the volatile organic compound, get rid of hazardous air pollutants altogether. Water-based paint can be substituted often into solvent-based lines. Or at least, I'm sorry. A traditional paint booth can be replaced with a water-based paint, right, without too much hassle. So it doesn't disrupt the operation. If I have a powder coating, suddenly I need voltage sources, and now I have to handle powder instead of liquids. That's a huge disruption if you want to go to an environmentally conscious coating application. So often, water-based process is more compatible with what people are already doing, right? So it improves safety and comfort, minimizes hazardous waste disposal. You can recover and reuse this stuff. It can also cost more. Biological problems increase. Foaming tendency goes up. And they can be runny, of course, and sag. So the plastic properties, they're more sensitive, right? More sensitive to humidity, of course, because they're water soluble, right? And sometimes it isn't possible to go from solvent coating. So that's why I corrected. If you need like stainless steel, for instance, to be resistant to water, you might have to change some fittings out. It's never convenient to change painting lines. Powder coating, which was brought up, here's a number of different ways to apply that powder. This is a fluidized bed. Basically, here you've got some electricity, and you heat up the part and introduce air. At the bottom here, it's a fluidized bed. So that paint powder gets kicked up. It's electrostatically attracted to the part, and then the part's heated up and forms a coating on the surface. Other ways, you can use a paint gun, do the same thing. In this case, the powder is pneumatically fed into the gun. There's basically an electrode here, a high voltage electrode. At the nozzle, it charges up the paint powder, and then you have the basic same electrostatic mechanism causing the paint to stick to the part. Even, it even wraps around here. That's what it's showing, right, because of the electrostatic force. And powders can be reclaimed relatively easily. This is a cyclone, basically allowing the capture of the powder here, pulling through a vacuum. So it's the difference between electroplating here, though, you can see there's no liquid transfer medium. It's actually quite a different process. But they both use voltage, and that's a key similarity. One of the major concerns with powder coating is the powder can clump. Right, so clumped parts, clogged lines. You can't get as good of a look out of powder coating yet. So it tends to be used more in industrial applications than consumer applications. Question?
A matte finish?
It's much more of a matte finish, exactly. Okay, so powder coatings, I think we've covered all these. It does save energy relative to what you need to run a solvent line, because now you need all sorts of capture mechanisms and personal protective gear and the like. It's very efficient. In a solvent spray booth, right, there's a ton of overspray and the paint gets everywhere. But here you can capture the powder and reuse it. And coating utilization up to 95 to 99% is possible. Usually when people actually run these lines, it's closer to 70. But you can get very high utilization. Right? The overspray is gone, no solvent vapors. It's good for the environment, good for protecting people's health. It's difficult to make small amounts of powder. So you have to make this powder in big batches for it to be economic. All right? It's not technically hard, it's economically hard. So you can't get small batches when you need it. And when you change color, you change the powder, all of its electrical characteristics change. So if I want to go from a green solvent-based paint to a blue solvent-based paint, it's not hard to do. I don't have to change capital equipment. I might have to clean some things out, but it's not a big deal. For powder coating, the process changed completely. The voltages, the application distances, things along these lines, the recovery, everything changes. So again, it's not as robust. Thin films are difficult to achieve. As I mentioned, the powder can clump. You have to preheat the substrate for the powder to stick and to get that film to cure. Okay, and here it is. Basically, everything we've covered from casting to cleaning to anodizing and conversion coating. Just get a sense of all the air emissions going out and all the resources going in. Basically, a summary plot here. The big picture story. Right. And of course, something for us to be aware of. About plastics, this will be an issue that actually you know a lot more about plastics than you think you do. That's why I'm going to blow through this, because you probably have seen plastics before in chemistry and in mechanical engineering. The industry is pretty big, about $9 billion industry if you look at mid-1990s numbers, just in terms of plastic parts. Widely used, of course, in electronics and healthcare, transportation products. And it's increasing, the use of plastics, because of our concerns about the environment. If we want transportation products to be light, good strength-to-weight ratio plastics will become used more. Powder coats are really plastics. Polymer coatings can be lubricants in manufacturing. In certain operations, you get rid of the cutting fluids. Just use a layer of essentially a plasticky coating. That serves as a lubricant. Fiber-reinforced composites, right? Familiar to some of you, especially in boating, right? And in other places. Fiber-reinforced plastics have good strength-to-weight ratios. Good for moving things around. There's a difference between plastics and polymers. And the key thing to know about the difference between plastics and polymers. Polymers are where chemistry meets engineering, right? So you take a polymer and you add things to it. You add colors to it, flame retardants to it, antioxidants to it, UV stabilizers to it, all sorts of additives to it. Then when it becomes useful for an engineering application, then it becomes a plastic. Okay? So that's the difference between plastics and polymers. Polymers, of course, are long-chain molecules. Here is ethylene. Okay? And under heat and pressure, you can have addition reaction, breaking in the case of ethylene, a double bond. So now each carbon can have a free bond. So if you've got a bunch of other ethylenes that have just undergone the same thing, they can hook up. Right? So we call the mer is the single unit. Right? That's what was derived from the ethylene. Right? This is now like an ethane, more like that. And these are just hooking up together. One thing that people typically don't realize is that the difference between ethylene, or polyethylene and polyvinyl chloride is minute on the mer scale. Here's PVC, polyvinyl chloride, right? Here's ethylene with a chloride, right? And then it's polymerized. It's not much difference there. Polystyrene you're familiar with, right, as an ingredient in styrofoam. Here's a 6-carbon chain here, but the basic double bond's the same. PTFE, polytetrafluoroethylene, ethylene, I'm sorry. Teflon is the name, you know that. But just replacing the hydrogens with fluoride, right? The same but different, right? All being polymerized in this sort of way. So if we break it down, we start with these mers. Then as we are creating the polymers, right, the polymerization reaction, we put in all sorts of additives. I'm going to talk more about these additives later. And the polymers can have certain characteristics. They can be straight chains or branched chains, or they can be amorphous. And I got some pictures on those coming up. But that's the difference really between thermoplastics, thermosets. Right? What's the difference between a thermoplastic and a thermoset?
One has cross bonds.
Yeah, the thermosets have the cross-linking, right, which really gives it different properties. Right? They don't really melt. Their properties aren't affected by temperature in the same way that thermoplastics are. I mean, we could have some fun right now with our plastic dinosaur here and melt it down and change its properties, squeeze the head and do do whatever we want to it. But with a thermoset, that wouldn't be possible. Okay? Elastomers are much the same. I'll talk about the difference between elastomers and thermosets in just a minute. Characteristics of polymers, right? This is beginning to come back to you. I can see it. Right? Longer chains or stronger chains, molecular weight, right? But controlling the polymerization reactions is an issue. Not every single mer is going to polymerize to the same degree. A higher degree of process control is required for more homogeneous chain length at the end of the day. And as was mentioned up here in the front, the more interactions between chains, the stronger the plastic. Okay, so we can talk about primary bonds, which link the mers together, and we can talk about secondary bonds, which are between chains. And we can talk about branched polymers that don't slide as much relative to one another. I'll show an example of that too. Those are stronger polymers. Okay? There are copolymers and terpolymers. Copolymer, one of the most famous ones, is ABS PC. Does anybody know what that's used for?
Tablets and telephones?
Well, that's ABS.
Oh, okay.
Oh, well, this is ABS is its own copolymer, terpolymer here, but there are also mixtures of ABS and PC. They're widely used in computer housings, right? And they can be turned into shingles. There was a big case study with a fast food chain that began using old computer housings to make shingles for their buildings, right? Styrene butadienes used in tires, yes, ABS. That's a hard one, right, for helmets, telephones. Here are some of the structures I talked about, linear, branched, right? If I've got these branches, the chains don't want to slide as much, right? So some branching can be good in certain applications. And then the cross-linking. And when you have a high degree of cross-linking, you've got a very strong, could be an epoxy, right, could be a rubber. Mentioned the difference between thermoplastics and thermosets. I won't say much more about it. Elastomers are different from thermosets in that they recover their shape fast. Right? You know that about rubber. That's why you use it for your tires, right? The return of the original shape when deformed, when the load is removed, is very quick. So it's a very fuzzy difference between thermosets and elastomers. But basically, you're thinking about things like silicone, epoxy, and rubber would be the boilerplate examples. Okay, and we mentioned It's not just about making the polymer, the polymerization reactions. It's about compounding, and compounding with additives. And here is what we call the ecological material flows, right? Plastic resins, when they are processed, are used often right back into the process. So you got plastic pellets that may be used in use. If you're injection molding a process, you've got these plastic pellets. Some fall on the ground. You're going to pick them up, put them back in the hopper. So there's process scrap, and that's built into the system. Of course, we can reuse plastic. We can remelt it. Or we can depolymerize, go right back to the MERS, and then build it back up again. To talk about an example, there was a polyethylene depolymerization plant in Cape Fear, North Carolina, that was built a few years back. But here are the additives, right? Here's what's being compounded. Lubricants, antioxidants for stability in contact with air. Anti-stats, plastics are not conductive. So if you want to keep charge from building up on the surface, and that can be really important sometimes, you don't want a spark to start a fire, there'll be anti-stats. If you're going to blow the plastic into a foam, like a polyurethane foam or styrofoam, there are blowing agents that will help that process along. Colorants, of course. Flame retardants. Brominated flame retardants are often used. These we will talk about in a few weeks. Have an impact on stratospheric ozone. They're also somewhat toxic. We talk about bromophenols, right? Organic, cyclic organics, phenols. Those are not good for human health, as are chlorinated paraffins. These are also harmful to human health. Heat stabilizers, peroxides to control the polymerization reactions, plasticizers that improve the plasticity of the product, so you can deform it without an inelastic deformation that doesn't recover. UV stabilizer. So you see, this is a real soup at the end of the day. And people often think of plastics as being very recyclable, right? But now think about these additives having to be compatible with each other, or different plastics with different melting points having to be compatible with each other. Turns out that plastics don't mix very well, if at all. So we've got concerns. You saw the toxics. We don't want to release those toxics during compounding, of course. The polymerization process, emissions, resource, scrap, waste. There's nothing inherently toxic or environmentally damaging about producing plastics, only when you're using additives of concern. So you might end up, depending on which flame retardant you're using, you might have phenol in your wastewater, right? And that's organic. It's very toxic, right? Phthalate would be another example, right? Or even metals, sometimes used as stabilizers or as colorants, right? So to the extent that you use harmful additives, and to the extent those additives can get out into wastewater or into the air, of course, there's concern. But generally, you don't hear much about people being concerned about plastics manufacturing so much. Not to say there aren't issues. You see, they're here. They tend to talk more about the use phase of the plastics, which can be good if we're talking about, again, transportation products, or end of life. Right? And if I remember, yeah, here, end of life. Right? Less than 4% of plastic is actually recycled. I think 3.5% is right. And 25% of the volume of all landfills is plastic. Right? So there's a cost and environmental effect associated with that. And now I put the plastics with the additives in the landfill, and then it rains. And what happens? These additives now can leach into groundwater. Right? Major concern there, especially if you're using chlorinated additives. Right? Now you've got organochlorines in the water that you have to contain. And if the containment of the landfill isn't good, or you just throw the plastic in the backyard, you're going to contaminate groundwater, right, or surface water. Okay, so plastic is a major concern from the end-of-life standpoint, especially. And if you incinerate it, especially under combustion conditions that are suboptimal, relatively low temperature, you can form dioxin. Dioxin is it's a fused organic that has a number of chlorine sites on it. It's one of the most toxic substances that we know of. Okay, so even parts per trillion dioxin people are very concerned about. Okay? But so we incinerate plastics, it can form dioxin, and of course, since there's metals in there, it can release metals too. Right? So incineration isn't a panacea here either. Right? Mentioned already, lead and cadmium in the colorants, stabilizers, and plasticizers. They can get out into groundwater. They can also get into the air if you're incinerating. Plastics can be depolymerized back into the MERS, so you can make a recycled plastic that's just as good as the virgin plastic. Right? And DuPont spent a lot of money to make a 100 million pound per year capacity pilot plant in North Carolina. So they used methanolysis, polyethylene into ethylene MERS, and then to build it back up into virgin polyethylene. It was great. Was robust to 10% other plastic. Okay, so it's a good robust process. Ultimately, it failed because the price of polyethylene crashed. It got cut in half between the time they planned to make the plant and by the time it was constructed. So they dismantled it for parts. Right, so you get the economics of recycling. And the infrastructure for recycling, too. You got all this plastic spread out all over the place. How do you get it to North Carolina? Are you going to drive it from California to North Carolina? And there's an infrastructure issue here, too. And if you don't have laws such as we've talked about, the home appliances recycling law in Japan, or the WEEE law or regulation, I should say, in Europe, you know, that infrastructure isn't there, the costs are high, and good attempts at recycling, even technically feasible attempts, can fall by the wayside in the economics, right? So what can you do? This was an interesting application that we saw in Japan, what they were doing. Instead of reducing in the processing of iron to make steel, remember we used coke as a combustion agent and as a reducing agent. And you have to go back to your notes maybe to recall that. Pulling the oxides out of the metal. So you have a reducing agent. We used coke, solid carbon fuel. Well, you can use plastic for the same purpose, which is a pretty neat idea. And plastic, of course, burns too, so it can be a combustion source. So that's one way, right, turning the waste into food, right, versus using virgin carbon sources from the ground. It also deals with the solid waste problem, of course, which they have no room for in Japan. You need a collection infrastructure. I mentioned that already. How do you sort these plastics? I'll say more about that later. Improving recycling chemistries, making them more robust to different additives. Right? But the economic drivers aren't there, and the energy drivers really aren't there either. And that's sort of the point here with this slide. This is the energy to produce, in this case, a certain volume of metal versus plastic. And you can see how much more energy it takes to make a certain volume of plastic than of metal than the same volume of plastic, right? So it's cheap stuff. It's plastic, right? So the drivers aren't really there, right? The recycling value of a soda bottle is less than a tenth that of the same mass of aluminum, right? By mass, and think the bottle is light, right? But there are reasons to go to plastics, of course. The strength-to-weight issue has come up a number of times in this class already. Composites have great strength-to-weight ratios. Unfortunately, you know, we don't use them in cars because it costs a lot of money, right? And we don't have as much experience in the manufacturing processes. But there's a belief, and if you go to Ashby's book on material selection and mechanical design, some of you might have taken a course or used this book, you know, talking about 10,000 BC. You know, mostly we were using polymers, so you could think of elastomers, things like wood. That should be under, papers here as a composite, right? Ceramics and stone. And here, up until about 1960, metals became more and more important as a percentage of material importance, right? This is obviously very qualitative. Think of the relative importance of metals versus polymers, composites, and ceramics. So metals are king up until about 1960, and the suggestion that the trend is going to move away towards high performance ceramics and plastics in a number of applications, right? So we'll see if it bears out. Probably to some degree true up until now. A lot of plastics development in the last 40 years or so. You've seen this slide already, and it just brings the point home. The energy to recycle The plastic is almost as much energy as it takes to produce virgin plastic. The drivers aren't necessarily there. They are there for metals, though. A lot less. We look at the ratio of secondary energy to recycle the plastic versus primary energy. The ratio is relatively low for metals, where it's relatively high for plastics. Right. Some more statistics about plastics. Really only polyethylene terephthalate, these soda bottles, and HDPE, which is pretty much milk jugs, so it's high-density polyethylene, are actually recycled to an appreciable extent. I mean, in theory, all plastics can be recovered 100%. Economically, no way. And only about 3.5%. Here's a number. Yeah, 9.3% of the mass of municipal solid waste is plastic, but that's 25% of the volume, right? Because other materials in landfills are more dense. All right, you've seen these chasing arrows. Some call the chasing arrows a hoax because only the polyethylene terephthalate and HDPE are recycled to any real extent, right? And there's even things you can do to these materials that make one chasing arrow one not compatible with another, right? So you need a very controlled stream. But just some statistics: 5% of the plastic mass produced, but 26% of the recovery is polyethylene terephthalate, soda bottles mostly. HDPE is about 21% of the plastic mass produced. About 6% of the is actually recovered. Right here. PVC pretty much is 0% recovery. This is used in credit cards, in pipes, PVC pipes, CPVC pipes in a lot of pollution prevention applications. Recycling equipment will use that. Household food wrap, PVC. Low density polyethylene, shopping bags, garbage bags, lids, cups. Very little recovery here. And it's about 32% of the mass produced is LDPE. Polypropylene, car batteries, margarine tubs, snack food wraps, right, like the plastic bag with 12 layers. That'll be a polypropylene layer in there usually. It's about 8%. Polystyrene, it's really a strange one, polystyrene. It really looks different in different applications, from packing peanuts to salad bowl lids to pharmaceutical bottles. So you wonder why it's difficult to sort out plastics. Well, you can look at plastics and you won't know if it's polycarbonate or if it's polystyrene, polypropylene versus polyethylene. These can be very difficult to distinguish. Right? And in fact, I think I've got, I'll come back to that point. You can't just, some of the issues associated with recycling, plastics can absorb oils and pesticides. So if you recycle polyethylene terephthalate in a bottle, in a soda bottle, you'll have to line the recycled material with virgin material. Okay, so like the soda bottles are not all recycled. It's sort of a sandwich of recycled material and then virgin material on the outside, because you don't want people drinking pesticides and oil. Right, so and it's a great plastic from the standpoint of gas transmission. PET is a very good barrier to gas transmission. And here's what I was talking about with plastics being mixed as we begin to come to a close here. One PVC bottle in 20,000 soda bottles can ruin the whole batch of 20,000 bottles. All right, so you got to find that needle in the haystack. It's not an easy thing to do, and polypropylene can be very difficult to distinguish from polyethylene, right? And polypropylene can have a similar effect on a batch of polyethylene, right? So you get to see some of the complications here. Here's a compatibility table. On the y-axis here, you've got the base material, and then adding a different type of plastic. Basically, what you're looking at is tolerance. So how much can plastics tolerate in terms of other plastics being mixed in? So if I look at polypropylene, it is intolerant of other in terms of recycling, even at less than 2%, which is what this graph shows. Right? Most of this table is dark, which means that plastics are insensitive, or are very sensitive to each other. Right? Polycarbonate tends to do an okay job in terms of recycling. You can see here in these rows. Here are the light boxes. But otherwise, it's pretty much everything's incompatible with everything. Right? And this is before we're talking about additives. I mentioned this already. What are you going to do with commingled plastics? Right? you make plastic lumber out of it. Right? Anybody seen plastic lumber before? Yeah, it's pretty cool. The insects don't eat it. Right? It looks all right. A little bit plastic, a little bit fake, I guess. But it's being used in Japan where there isn't a lot of lumber. PVC, because of that chlorine in there, sensors have been developed now so you can find that one PVC bottle in that 20,000. So actually, there's quite a bit of PVC recycling going on in Japan right now. In fact, they'll go to old construction sites, and PVC is used in pipes. So they'll take the old pipe from the building and then use it from a high-pressure application to a low-pressure application, right? Because as it ages and as you recycle it, it becomes weaker. So you wouldn't want to use it in a high-pressure application, but you don't have to downcycle it much. You can just put it right back into a drain instead of a pressure line. Right? So there's quite a bit of work going on, and most of it, again, in the plastics arena is in Japan. And it's driven by end of life and lack of ability to landfill and where you're going to put an incinerator when it's built up everywhere. Okay. Might say a few more words about plastics, but I think this pretty much took us to the end. And I'm going to start with this example. It's a nice transition from plastics, say a few words about electronics, and then energy associated with it. We're really going to be talking about combustion for almost the whole class period on Friday. Okay, so thanks a lot, and we'll see you then. We're just finishing up with polymers, and I guess I'd pose the question to the class. What did we, I guess, conclude, if anything, about the environmental impact of plastics? What is it that we're most worried about? Is there anything we can point to or any group of things we can point to? It's plastic.
As recyclable as people think.
Yeah, they're certainly not as recyclable as people think. And so what? Okay, so that's the reason why that they're not as recyclable as people think. But so what if we don't recycle the plastic? Why do we care about recycling? Okay, so it takes up a lot of landfill space. Okay, is that a problem in and of itself?
Only as long as all the chemicals stay in the landfill, it's not a problem.
Yeah, that's certainly an issue. And if you've got landfill space, that's another issue, right? Are there bigger issues associated with plastics?
It's the resources.
Okay, petroleum, we're going to talk a lot about petroleum today, and we'll see where most of that goes. It's not into making plastics per se, but certainly it is exacerbating a little bit of problem that exists in terms of petroleum consumption for sure.
Well, there have been questions about using it in food containers.
Recycled material?
No, something it produces is a lot like the estrogen molecule.
Sure, so there are some health issues associated with plastics that people haven't been able to pin down yet. Are plastics good for anything? Yeah, I mean, look around, right? I mean, it's really a key element of modern society, right? And we should think, especially in the resource consumption issue, that plastics conserve a lot of resources too, right? If we look at petroleum and the ability to use plastics to lightweight a vehicle, certainly they're worth more than their weight in terms of the fuel that's consumed in the vehicle over its lifetime, right? So lightweighting is a very important aspect of plastics. So the plastics industry will say, well, they've got a bad rap. And to some extent, they can make a case for this, especially when we're talking about transportation products. We have to know which category of waste we're talking about. We talked about solid waste and resource consumption. How about air emissions associated with plastics? Are there any?
If you burn them.
If you burn them, right? And we talked about if you don't have a good incinerator, what will happen is the formation of dioxins, right? And we talked about brominated flame retardants, we'll talk a lot more about in a few weeks, and their relationship to ozone depletion. Okay, so it's about time as we prepare for the first exam in 10 days to start putting your arms around these issues, right, and taking a step back. Right, metals, plastics, we'll talk about energy consumption today. But if we're talking about environmentally benign polymer processing, right, what we're really talking about here is largely a solid waste issue. We need technology for sorting and recycling and standardization for recycled materials, right? The red dinosaur and the yellow dinosaur need to be compatible at the end of life so we can recycle that material. Design innovation, of course, most of our mechanical engineers who come through our undergraduate program don't know anything about designing for plastics, right? And that's a niche area in professional development that we have to do better on, because certainly they have their applications that are beneficial to the environment. Right, viable recycling scenarios for composites. Right, we talked about the issues there, separation, and process optimization and energy efficiency, as we would talk about with any type of material processing. It comes back to the old radiator. Right, we looked at this problem earlier in the semester here with the grill. Right, composite versus galvanized steel. Right, what can the plastic do for us in these transportation products? Right. And what could it do for us in a cell phone? Okay, this is a comparison of a DRAM chip. This is one computer chip and the life cycle of a cell phone. The computer chip was produced, or I should say was analyzed in an article in Environmental Science and Technology back in December of 2002. And basically tracked the energy and water consumption associated with this 2-gram DRAM chip. It turns out that the footprint of this DRAM chip is about 1.7 kilograms. So a 2-gram chip using about 1.7 kilograms of resources. We can compare it to a cell phone. This is some work that we did along with colleagues at the Technical University of Berlin. And of course, we know that there are quite a bit of plastics used in cell phones, right? This is my particular cell phone here. It was a different one than what we analyzed in this life cycle analysis, right? So which has a greater, let's talk about energy here, energy utilization, the computer chip or the cell phones? Anybody want to vote? Who votes for the computer chip? Everybody voting for the phone?
You mean in the production, or you mean in the usage?
Life cycle.
I'll vote for the computer chip.
So one vote for the computer chip.
Computer chip.
All right, got a few? Okay. This is a special computer chip. There are ordinary computer chips, and then there's some higher intensity. Like you think a microprocessor or a memory chip might be more elaborate than just, say, an ordinary set of and/or gates. Right? You might remember from electrical engineering class. This is a special kind here. Now, a cell phone, of course, contains about 42 ordinary chips. That might include DRAM, right? But let's look at the scope of the life cycle here of that computer chip. You start with silicon metal, right? You have to purify it, so there's some chemicals called chlorosilanes that are used that are particularly toxic. That produces polysilicon, some of which could be used for solar cells. But this just gets you to the substrate stage. Now, what we're going to do is pattern various different elements into the wafers themselves using chemicals, water, and very pure gases prior to assembly and arriving at that microchip. Now, this would be basically a partial. So the gray arrows here are the partial accountings of the energy. The black arrows are full accountings, and the hollow arrows are not accounted for in this study. This is the cell phone. And what you see here is a display printed wiring board. So there is a board beneath this LCD screen. There's the main printed wiring board, right, where the chips are located. So they're here listed as semiconductors. Of course, you've got a display and an antenna and a keypad and a microphone. All of this gets assembled together within this plastic housing. Okay? then of course it reaches the customer, and we talked a little bit about remanufacturing of these cell phones. Could be disposed of in a landfill, could be recycled. Okay, so this is the life cycle of a phone. And what we looked at was for these auxiliary, the display module, the antenna, we only looked at the materials. We didn't look at the semiconductors because we're comparing it to that single DRAM chip. Okay. So here's the conclusion of the investigation. Now, the DRAM is not a higher energy utilization than the rest of the phone, but it's pretty darn close for being one chip. In fact, for a normal user of a cell phone over 2 years, just the production of that DRAM chip is almost the same. Okay, and if you unplug your charger, this bar will actually come down quite a bit below that of the DRAM. It turns out that most of the energy consumption of a cell phone is related to leaving the charger in the wall. So you pull that out, and you can get this number down quite a bit. But here's the printed wiring board. Now, we haven't talked much about electronics yet. We're going to thread it into the rest of the course here. But you can see high energy consumption associated with the printed wiring board fabrication and those materials. Okay? So what do you know about the production of plastics? Coming back to topic here. What did we say about the primary production of plastics? Does it take a lot of energy? Do you think that's a large component of this bar here? Or was it the metals, right? The gold, the lead, solder, the copper, right? So it's not necessarily the plastic content that's driving this. So what is the impact of the plastic used in this phone? Do we care about it? Would you care? Why is the plastic environmentally important, if at all, in this phone? We got a polycarbonate screen here, right? Probably some ABS pieces of fiberglass inside. Do you care? Who votes for no? Who votes for yes? Who doesn't know? Well, let me come back to the answer. Think about it a little bit more. All right? Here are the chips, by the way. A typical computer chip. Now, that DRAM I mentioned was a special chip. It's about, I think, 42 megajoules to produce. A typical chip will only require about 10 megajoules to produce. Now, I say only 10 megajoules. That's quite a bit of energy, actually, for one computer chip. Remember, this phone has about 42. So if I use that 10 megajoules as an average, right, the chips really do dominate, right? So here's our graphic, right? Drive the point home a little bit, right? So the chips do matter. So how can I minimize, forget about the plastic for a minute, how can I minimize the life cycle environmental impact of a phone? What can I do about this?
Reuse them more.
Reuse it? Well, no, I want a color screen. This one doesn't have a color screen, and I want a camera.
Why? you can try to use the case and design the other elements around it.
Use the case and design the other elements around it. But the fact is, and we see the data here, that the case is a very small impact here, right? Maybe I could reuse the battery. Maybe not. I might need a higher energy storage capacity for my camera, right? Or if I want to take video, or save more phone numbers, or run color on this, right? Color screen is going to consume more energy.
Can you reuse the chips?
Yeah, sure. I could reuse the whole thing, right? I mean, why do people get rid of cell phones?
Style.
Style. So there's a stylistic element to this. There's also a technology element. New features, and sometimes, yeah, they just don't like the look of it anymore. It's too big, right? So they'll go for the latest style.
Sprint.
Don't they break? I mean, most
They
people
do
I
break.
know buy them because they drop them or drop them in the water. And
It's very rare.
Really?
Very rare. You're traveling in different circles than
Okay.
the mainstream, and certainly this industry wouldn't survive
Sorry.
with people like you, right? Right. We need to spend more. Actually, the big driver is, I mean, certainly they do break, but the big driver is stylistic obsolescence and technological obsolescence, right? And you can say, well, remanufacture the phone, right? Look what would happen if we remanufacture the phone. Here's the energy consumption of 2 cell phones over the life cycle. Okay, and of course, if you remanufacture one of them, right, that impact goes way down because most of the energy went into producing the materials, not the use phase, right? If I reuse a car versus remanufacture a car, it turns out that I'll be using a lot more energy, right, because cars generally become more fuel efficient, right, if we're talking about the same type of vehicle, right? But it's different in electronics. This is the point, that the manufacturing has a much larger burden as a percentage of the life cycle than, say, manufacturing operations for a car. Okay? Doesn't mean that manufacturing and traditional fabricated metal products manufacturing isn't important. We've talked about all the environmental concerns there. We've talked about the magnitude of the problem. Right? But as percentage of the life cycle for a single product, manufacturing dominates. So remanufacturing is, the processes of remanufacturing don't even show up here because they're so minimal in terms of energy consumption relative to the production of the phone in the first place. But there's a real problem here, right? Because you're not going to remanufacture my phone and sell it to people who are craving color screens and cameras for the same reason why I got rid of mine in the first place, right? And we talked about this issue before, the sustainability question, right? Who's going to buy that phone? Diffusion in developing countries, right? They need cell phones too. And this is an economical way to provide them, right? So now I come back to the question, is the plastic important? Anybody want to change their answer? Again, the plastic doesn't show up in the original manufacturing, doesn't show up in the use phase. The recycling value is minimal. It's all about the metals.
Can I ask a question about that graph? I'm not sure I understand. There's a recycling area that's pink and a remanufacturing area that's purple, and then there's recycling and remanufacturing at the bottom. What?
Let me break this down for you.
Yeah, please.
The point here is the magnitudes. You can break it down further when you take a look at it online. But the point is, this is chip fabrication. The yellow here is the materials. The red here is the printed wiring board manufacturing. And then the blue at the bottom is the use phase. This is the energy consumption for 2 cell phones. Okay, so you see the use is relatively low. I've produced 2 cell phones, and that's why this bar is so big. The recycling benefit is minimal from an energy standpoint, and that's what I think you're confused about. And the fact is that if you recycle the material, you do get some gain, but the fact is it's these productions, semiconductor manufacturing process, the purity of the material that's required. Right? If I recycle the plastic, I don't get much back. I technically can't recycle chips, right? So there are some precious metals here, and you will recover them. Technologically, you can't get much more than 50% of the metal content back out yet until the technology advances more. So recycling doesn't do much, right? It's about remanufacturing if you want to minimize that impact over 2 life cycles. Of course, there's an economic question there, right? So what I'm trying to get somebody to say is that remanufacturing is all about the plastic. Come back to this phone. If I'm going to take this apart and test it and maybe put a new housing on it or repair some parts internally, I better be able to disassemble it. The disassembly is related to the geometry, and that's a lot to do with the plastic in terms of its form. Not necessarily in terms of the plastic content, but in terms of the form and the disassemblability. We're going to talk a lot about that later in the term. Right? So it turns out the plastics are important, and how we can work with plastics and understanding how to make housings and assemblies, right? Or even whether it's a flip style or a candy bar style for the cell phone is going to make a world of difference in terms of the remanufacturability. Right? So now as a segue to topics in the future, it's not so much about the plastics manufacturing industry, right? There are environmental impacts, and we talked about it. It's a lot more what you do with the plastics and where they end up, right? How they're used. Okay, and that's considerably different than, say, semiconductor manufacturing, metals manufacturing, or the transportation industry in general. Okay. So I definitely wanted to finish up on plastics with that point. And here's a concept that we worked on with our colleagues at the Technical University of Berlin, a paper we're going to present in Tokyo in December. This is a modular housing platform. This was produced by a student named Marco Zetzel, a visiting student from Berlin. He was here for about 6 months working in my lab. And basically, this is a phone that can include the housings of 7 or 8 different models. Okay? Probably more, but we've tested it with that many. So basically what we did is we took some discarded phones, pulled out the insides, and put them into a new housing. Okay, so the sticker here is a little bit chintzy. Of course, the buttons weren't. This is rapid prototype. Okay, so these aren't the actual end-use materials that we'd use. But we were able to disassemble these phones, put them into a new housing. And the housing isn't that ugly, right? We could work a little bit on the style. But what we wanted to do was to prove that it is possible to come up with a single housing that can accommodate the net functionality from the previous incarnations of different cell phones. All right, so now if I were a company, and we're actually kicking this idea around a little bit, we could take old phones, put our own brand, our own housing on it, and resell them, right? This would be a much more economical way to do it than trying to have a different process for every phone, right? Single process for many phones, right? So just an idea here. And this is how the inside works. So you basically, we've got some foam inserts. And there's some real challenges here because different batteries, different SIM cards, different fixtures to the circuit board, different sizes of internal components, different places where the buttons land. That's what this is showing here. For 3 phones, we basically mapped them all together. And we had to design the buttons so they would be able to accommodate all 3 circuit boards and the button targets here. Okay. So you get the idea. It's a top-down assembly. And we call this a MHP, Modular Housing Platform. But we aren't too worried about the plastic. Certainly the investment in this plastic material is minimal compared to what we're recovering, right, and what we're enabling. Right. So it's time, as we begin preparing for the exam, right, we talk a lot of detail in a lot of different areas up until now. But on the exam, you might be asked some much bigger picture questions, synthesizing these blocks that we've put together. Right, so I challenge you to think a little bit. I'm currently working on the study guide right now. I hope to have it for you by Tuesday for sure, maybe earlier in the weekend. Okay, so we're going to talk a little bit about energy, but I want to answer any questions before we do that. Any before we get going? In the back.
I don't know if this will change our answer. One of the drivers you said for the remanufacturing for cell phones.
Talk a little bit louder.
One of the drivers for the remanufacturing for cell phones was that developing countries have a need, they don't have them, and so they'll need them, and so the net energy of remanufacturing one versus starting one from scratch is less.
It's negligible.
Theoretical.
No, not theoretically.
No.
In practice, we measure.
Here's my question. Theoretically, if everyone in the world had a cell phone, would that change our answer?
Absolutely. There wouldn't be a market for remanufactured phones in that sense, unless they were so tiered. But a very small fraction. I don't know the fraction of people. I know half the people in the world don't even have electricity. And, 6% have a PC, so it's somewhere in between. It's probably closer to 10 than 50 for sure. Communication is related to democracy. It's related to the development of infrastructure and jobs that generally aren't available in large portions of Africa, South America, and Asia in particular. Right? So we've got a long way to go before we have to worry about it, but certainly the point's well taken. Then you would start worried about specifically energy consumption in use and getting them to last as long as possible. That's a good point. Other questions or comments?
Why do we always assume that in the developing countries that they want something less than what we have?
They don't want anything less than we have. I don't think anybody's assuming that. I would hate. I've never seen anybody admit that. I mean, maybe implicitly, right? But you can't just snap your fingers and say, well, Africa is going to have the same standard of living as America, as we know, right? I mean, it's being realistic that development happens over time. And that development needs to leapfrog a lot of stages. Actually, I'm going to come back to this point, especially when we talk about energy, because what we're going to see is a lot of the energy in the future is going to be consumed by the developing countries, not the developed countries. And that's really going to change the dynamic tremendously. And if they go through the same polluting path and the same length of time, they'll probably be a lot unhappier if it takes them 200 years to reach the same level of development that we're at. Especially with television and radio, and people know how other people are living. It's probably not sustainable. So this leapfrogging concept is critical, right? And I think people are aware of it, but they're also realistic too, in that these things happen in steps. But it's a good point.
You can also think about the fact that there are a very small number of consumers in the United States who would love to have a recycled phone to save money or because it's recycled.
That too, actually. It is a niche market.
Right.
And it's observed more in Germany, actually, than the United States. But there is demand.
Right. So if
Right.
there's demand in a developed country, then there can be demand in an undeveloped country. And they're not getting less than what those consumers want.
In that sense. And if you can make the phone look cool, and that was the whole point of the MHP here, because certainly the, and this isn't the stylistically most attractive phone, and we can certainly work on it. But certainly the concept that you could take the guts of beat-up phones and make them look brand new and deliver them at a low cost would have this appeal, right? And they might not even know the difference, right? A lot of laser toner cartridges, the phones that you buy, the disposable phones that you buy, are 87% recycled, right? And we're not sensing that that's somehow something less or that we're getting something inferior, right? So it's, the packaging, how you deliver it, makes a big difference.